Excellent. Yeah. So thanks very much for the intro, Nick. I feel like you've done part of my job for me by getting the excitement going for renewables. So yeah, I'm excited to give this talk, and actually it feels like a little bit of a homecoming for me. I actually used to help out at Bristech. I never really imagined that when I was giving a talk, it would be a virtual talk. Amongst a COVID-ridden planet, but hey, here we are. You take what you can get, and yeah, I'm excited to share with you why we're really enthusiastic about wind energy. And so first, I'll just tell you a little bit about BitBloom. Who are we, and why do I feel qualified to tell you about wind energy? So BitBloom are if I can get my slides turning, yeah, so we're a relatively new company. So we were formed at the end of last year, and the three founders of BitBloom have over 40 years of experience building tools and products and solving hard data and modeling problems in renewables. And so, yeah, as I said, grown from 3 people at the start of this year, and we're soon to be 7 people, and so we're really excited about the opportunities in renewables and wind energy, and we're building software products and answering hard questions that are asked by our wind energy clients. And so for me personally, I've spent my career building software for experts to solve hard problems. And software is great and all, but I believe it's only by coupling great software with great people that we can do great things. So speaking of great things, why wind energy? So why does this stuff make us want to get out of bed and solve problems? So firstly, and Nick's already mentioned this, is our planet. Despite recent events, climate change is still the biggest threat to life on our planet, and wind energy is an important tool in the toolbox to solve that problem. And by tackling the hard problems in wind energy, we can make it a viable part of the energy system. But it doesn't just make environmental sense. It also makes a lot of economic sense. So this is the growth in wind energy installed capacity since 1980, when the first wind farm was built. And you don't get growth like this without serious economic benefits. So onshore wind is the cheapest source of energy, certainly in Europe, and it's becoming the cheapest source of energy worldwide. And so at the top of this chart at 2019, last year, that's 650 gigawatts, which is enough to power hundreds of millions of homes. And everywhere in the world is getting in on the act. Everyone knows that wind energy is a viable part of our energy systems. So China has certainly been leading the way here. Europe is pretty good too. Noticeably absent is Russia, which is a bit of a shame. I assume it's just a bit too easy for them to burn the stuff that they have in the ground. But never mind, we can carry on without them. So a few big numbers here. So 366 gigawatts. That's the amount of installed capacity forecast by 2024, between 2019 and 2024. So that's a 50% increase on what we have today. So it's still growing pretty fast. 6 million jobs supported by the wind industry in 2050. So this is obviously a forecast, and who knows what the number will be. But if that's correct, then that's 1 in every 700 to 800 working age adults, which is a substantial portion of the world's population working in wind energy. 4.5 million homes powered by Dogger Bank, which is one of the biggest ongoing energy projects, or the biggest upcoming energy projects over the next few years. So that's 1/6 of all, 1 in every 6 households in the UK powered by this single wind farm. It's actually 4 wind farms, but it's a complex of wind farms. And then 67 days, which is the record coal-free streak in the UK, and that was set this year. And these records are tumbling all the time. Every year, this record is broken, and this is pretty cool. And this is what it's all about. It's all about not burning the things in the ground to make our energy. And so just to give you an idea of what these things look like, at least from space anyway. So this is London Array. So this is, it's rather the Thames Estuary, and there's a number of wind farms here. So London Array, for example, and this might be hard for you guys at home to see, but I'll zoom in a little bit here. Hopefully you can see the individual turbines here. So this wind farm is 175 turbines and generates 630 megawatts at its peak, and it's 122 kilometers squared. So in 2013, when this was commissioned, this was the largest wind farm, offshore wind farm in the world. And it's pretty cool that that's in the UK, and we're still a world leader in offshore wind. That is pretty cool, but some of the upcoming farms. So this is a screenshot from 4C Offshore, and this is a great website. If you're interested or you want to geek out a little bit on what's upcoming in the world of offshore wind energy, then 4C Offshore have a great map that you can explore and get all kinds of info about these wind farms. So let's zoom in on the Thames Estuary again. So you can see this one is London Array that we were just looking at. So remember that in 2018, this was still the largest offshore wind farm in the world. Look at the size of some of these that are going to be developed. So these four up here comprise Dogger Bank. So there's 4 separate wind farms, but it's all part of a single development plan. And Dogger Bank will be over 2,000 kilometers squared. London Array, 122, Dogger Bank, 2,000 kilometers squared, and it will be 4.5 gigawatts. So I mentioned earlier that that's 4.5 million UK homes that will be powering. So the size of these things is just amazing. And that's pretty cool, but I don't think that's the coolest thing about wind energy. So the turbines themselves are amazing. So in 1990, the largest turbine you could probably get your hands on was 50 kilowatts, and it was less than 40 meters rotor diameter. So comparing that to what we have today, commonly, well, not commonly, that this is a pretty big wind turbine, but a option if you're building your onshore or offshore wind farm is this 8 megawatt Vestas machine, which is 164 meters rotor diameter. In 4 years' time, we expect to be seeing this 14 megawatt, 222 meter wind turbine from Siemens Gamesa, and that is already confirmed for use in one of the Dogger Bank complex wind farms. So they're big. Just to give you an idea how big, this is that Vestas platform, the 164 meter turbine. 164 meters is hard to get your head around, but it's big enough to fit 2 Boeing 747s tip to tail across the rotor diameter. I mean, that's pretty big. That's cool. So one consequence of the size of these turbines is the amount of air that flows through them. So at 13 meters a second, which is the rated wind speed for a lot of turbines, that means 350,000 kilograms of air are going through this rotor, the swept area of the rotor every second. I mean, that's awesome. And that also happens to be roughly equivalent to a single Boeing 747 passing through the rotor every second. That's a nice coincidence, isn't it? It makes for a nice slide anyway. But yeah, that's pretty cool, I think. So they're pretty wicked pieces of engineering, and they're built to last as well. So a turbine might be certified to run, so that is it will run continuously or almost continuously for 20, 25, or even 30 years, and in extremely harsh conditions. So the whole point is to put them somewhere where it's windy. So these things are going to get battered about. And to put that into context, a typical family car, if you're lucky, might run for 200,000 miles. And let's just assume an average speed of 50 miles an hour. That's about 167 days, or less than half a year. So you buy a car and it runs for less than half a year. You buy a wind turbine, it runs for up to 30 years. I mean, that's really nice, and it makes me feel, pretty in awe when we're working with these machines. So hopefully that's got you a little bit excited about wind energy and why it's cool. But why I'm here to talk about data. So why analyze the wind farm data? So let's put this in financial terms, in monetary terms. So a typical 500 megawatts. So if you remember, the London array was something just over 600 megawatts. So this is a large farm, but these days fairly common. Generates almost 110 million pounds of electricity annually for its owner. So this is based on some, reasonably conservative assumptions. So one thing that we do as analysts in our company is we try and increase the energy produced by a wind farm. A typical project of this sort might produce a 0.5% increase in energy production, which is worth £550,000 to the owner. So that might give you an idea that this is worth doing. One way we might do that is through performance optimization. So how does that work? Well, we might identify turbine underperformance. So looking through the data, we can find which turbines are underperforming and in what conditions. And that might be due to signal calibration issues or controller strategies. And we can make a recommendation to the owner to go and take a look at that and go and fix it. But we do other things as well. So one thing we do is value estimation. So these wind farms change hands quite frequently for fairly substantial sums of money. So if an investor is interested in buying a wind farm, they want to know what it's worth, how much money it's generating. And what we can do is to look at the data and reduce the uncertainty on that value estimation. So, taking into account conditions and other things, like environmental conditions. So this increases the investor confidence and lowers the cost of borrowing, and increases the viability of and attractiveness of these projects. One other thing that we might do is warranty verification. So turbines come with a warranty that guarantees a minimum level of power production for a given site conditions, and we can look at the data and identify if that warranty is being met. And if it's not, then we can recommend that the owner goes back to the manufacturer and gets a bit of money for it. So we can also lower costs, and this is increasingly what we're trying to do. And one way we can do that is by predicting failures of turbines. So these are pretty cool pieces of kit, but they do have a lot of components that fail from time to time. We can try to predict when that might happen and schedule maintenance of those wind turbines before those problems occur. And increasingly, we can try to ensure that maintenance occurs at a time when energy capture is lower, so at a time when there is just low wind. In future, we'd like to integrate into kind of logistic operations and supply chain optimization, and make sure that the correct tools and parts and everything are in the right place at the right time to further lower the costs, and maybe even automate these procedures so that they're whatever can be is carried out by drones, for example. So let's take a look at the data. So what do we have to work with in order to solve these problems? So firstly, we've got the structured time series data. So this is any data produced by machines, and those machines are wind turbines, met masts, substations, meters, and the power grid itself. So all of these machines and components in the system produce time series data. So commonly for us, that's one data point every 10 minutes. Of course, it's produced at a higher frequency, but we look at the lower frequency data. There's unstructured event data, so that can be anything from software logs to human scribbles. So this might be produced by service technicians, operators, controller events, control software updates and faults. And then there's hidden data, and this is data which isn't immediately available, but that we need to derive through data analysis techniques or further site research. And this might be terrain or forest cover, and this might affect the turbulence levels at a site, which would again affect energy capture or potentially the amount of damage that a wind farm, a wind turbine is receiving. So let's zero in on a single wind turbine and take a look at what data might be available from here. So this is a schematic of a typical wind turbine. Of course, there are lots of different models available, but a lot of them do follow this common kind of design. So a lot of these components are common across a number of different turbines. There are different models, like you might get a direct drive turbine, which won't have a gearbox, but let's use this as an example. So a lot of components here, and each of those components is going to have multiple sensors attached, which we can potentially access, although of course not always. But let's just take one of these systems, for example. So the pitch system. So the pitch system is what is used to rotate the blades to fine or feather angles in order to optimize the energy capture for the turbine. So this system might have a whole range of signals. So the pitch angle itself, the pitch rate, the current to the pitch motor, the temperature of the pitch motor, the temperature of the pitch motor heat sink, the controller, pitch angle set point, the grease level, the grease pump status. So a whole load of signals, and each blade will have all of these signals, and then it might also have like statistics for those signals, like the minimum and maximum over the previous 10 minutes and the standard deviation. So that adds up to a lot of signals. In fact, I did some quick numbers, and a typical data analysis project might have 25,000 unique wind turbine data signals. So this is a hefty wad of data to work through here. 100 plus supporting signals, including the Met mast. So a Met mast, I should probably explain, is a mast that gathers weather data like the wind speed and wind direction. So a load of supporting signals as well. 500,000 discrete time points. So this is, let's assume that we're looking at 10 years worth of data for a wind farm, which is typical for an analysis project. And 100,000 unstructured events. Could be more or less depending on how many we have access to for a particular project. So this is a quite overwhelming amount of data, and it's not huge volumes. It's not like really big data, but considering that this data isn't always the best quality, it's quite a lot. So what is our approach? Our approach is to build standard tools for our analysts and for analysts in other companies to use that do all of the routine tasks for them and make that easy. So here's a slide which is hopefully the only slide in the presentation that looks like an advert. I promise I'm not trying to sell you anything, but this is what we do. This is what we build. We built Sept, and this is an analysis product too. And our vision is really to provide high quality and high performing implementations of all of the day-to-day activities performed by data analysts, and facilitate that rich and intuitive data exploration. So we want all of those data signals to be available to them like on tap, so that they can just dive in and see what's there. So our kind of philosophy is that this frees them up, frees experts up to use their creativity to develop new models and algorithms in order to detect new kinds of problems. So what kind of challenges do we face apart from just all of these data signals? So firstly, and forgive the rather fuzzy picture of a SCADA control room, but this is meant to show kind of data collection, and there is really no standard approach to data collection within the industry. It's almost an afterthought, if it's even a thought at all. So almost every time you come to an analysis project, you have to rethink the way that you do data ingress into your system. So of course, this is a common problem with many kind of fields of data analysis. Just to give you a flavor of the kind of things we have to deal with, these kind of data formats can be just raw SCADA data streams, CSV files, Microsoft Access databases, Microsoft Excel spreadsheets, SQL databases of all different flavors, OPC systems. So our approach is to standardize the way that all of this data comes in. We've built adapters into our product so that the analyst just doesn't really have to think about this stuff. And we're also helped out these days by asset management systems. So there are a number of products on the market which provide APIs that we can integrate with in order to make this kind of data ingress easier. But that's really only started to happen in the last sort of 5 years, and they're only being opened up in the last few years. So so things are moving in the right direction. So once the data's into our system, what might it look like? So here you can see a typical power curve. So that's wind speed on the x-axis and power on the y-axis. So we're used to seeing these all the time dealing with wind energy, but I'll just explain what's going on here. So at low speed, the turbine doesn't operate, so that's like less than 3 meters a second. And then between about 6 meters a second and 13 meters a second, energy capture increases almost linearly. And then from there onwards, the turbine generates its maximum power. So that's called its rated power. So here that looks like it's 2,800 kilowatts, so 2.8 megawatt turbine. And then at really high speed, it shuts down because it can't operate. And one of the things that we want to do with this data is to be able to classify and understand every single point in this plot, and in order that we can provide owners and operators with an understanding of exactly how their assets are performing. So let's take a closer look at a couple of these things. So what's going on here? Is this a low power mode? I mean, maybe. It looks like it, but why is it happening? Why is this low power mode happening? So this might be curtailment that's enforced by the grid. It might be a controller fault. It might be some maintenance issue, or a different, someone who's been tinkering with the turbine has accidentally put it into a different mode. So we want to know why that's happening. There's an even lower power mode here. So what's going on there? What's all this here? It looks like noise, but is it noise, or is it faults? Or maybe it's just transitions between one data point and the next. So remember, we have 10-minute data, so this could be a point which occurred halfway. Half of that 10-minute period was at a high speed, and half of it was at a low speed. And then finally, the classic "who turned off my turbine?" So normally there's a good reason for this, but actually quite frequently there isn't, and we want to be able to understand and pick up on any faults that are happening. So that data is a bit messy, and here's the thing about those sensors. So they're not that great. One example is you can see on the back of this Vestas turbine, there's an instrument. That's an anemometer, and that's placed there to collect information on the wind speed and the wind direction. That's not really a great place to collect wind speed and wind direction information. It's right behind the nacelle, so that data is going to be pretty messed up. And this is a problem with a lot of the data that we get from turbines. Historically, turbines are not really built to collect reliable data. The data is just a byproduct of operating a wind farm. So that anemometer there is really feeding information to the wind turbine controller to make sure that it operates in the right mode, and that the things like the blades are pitched correctly, for example. So we need to do quite a lot of treatment on that data, and the solution is, of course, to use statistical techniques and do the kind of data analysis approaches to rebuild the data and make sure that we get reliable signals. And yeah, we build all of that into our software so that the analysts can kind of ignore all of that stuff and just get on with the really creative stuff. Another problem, so there's a lot of different turbine models, and they all have different performance characteristics. But almost the bigger problem is when two turbine models that appear identical have completely different performance characteristics. So they can be placed right next to each other and perform completely differently. And there's a bunch of reasons why that could happen. So they have to endure pretty harsh conditions. I said earlier that, you know, these things are made to be put in windy places. So we, you know, they're going to be battered around a bit. So they can endure storms, gusts of wind and ice, so that the blades can become completely iced up. And also, almost a bigger issue is that manufacturing variability means that components in the wind turbine get replaced at different times. And so, yeah, this all results in completely different performance characteristics. So what's the solution to that? The solution is just experience and well, that's part of the solution anyway. So the experience to know when a turbine is operating, or what might have happened to a turbine, to make it operate in such a way. But we can codify that kind of experience, and, you know, once it's been discovered once, we can we try and use our software to generate algorithms in order to detect these kind of things automatically. And of course, we can build clever models as well. Increasingly, we're looking towards machine learning, but also physical models in order to detect these kind of performance anomalies. Finally, on kind of challenges that we face, is just the low frequency of the data that we get, and of course this makes it easier to deal with the data, but we just miss out on a lot of the kind of high frequency effects that we can, or things that we can induce from high frequency data. So you're probably quite used to hearing about, like, you know, big sexy volumes of data, like trillions of data points a day being processed by Kafka clusters. So we're a long way away from that. We have something like one data point every 10 minutes. I mentioned you might get the standard deviation, the minimum and maximum of that signal if you're lucky. And the reasons for this are just that the systems are old, the systems are in remote locations, and there's just a lack of incentive from the owners and the operators to provide that data. So more modern wind farms are starting to come around to higher frequency data, but actually we can use approaches to try to fill in what those high frequency effects might be. And I'll show an example in just a moment. So yeah, what future challenges are we going to face? So here's a picture of a super old wind farm, and that's just kind of trying to illustrate the fact that there are old wind farms out there. And when a wind farm reaches the end of its life, there's a decision to be made. Do you repower? And that means, do you replace all of the turbines with new turbines, swanky new turbines that are going to generate more power, or do you try to extend their life? Life extension might be an option in the case that the conditions that a turbine has undergone are less than the designed lifetime. And so we can use some data analysis and machine learning techniques to tell us the answer. So, I've got another slide that looks like an advert here, but here's one of our products, Damage Prospector. And so with this, we're using high fidelity aeroelastic simulations of the turbine. So this produces high frequency data, and we use that to create a training set with loads and damage information in it. And then we can apply that data set onto the SCADA data, so the 10-minute data, using machine learning model. And this allows us to do cool things like analyze the lifetime of each individual turbine, how much of its lifetime it's used up, and also what conditions are most damaging to the turbine. So which wind directions and which wind speeds are causing the most damage. And so this information can inform life extension, as I mentioned, but also kind of control the strategies to extend and preserve turbine life. Another future issue that we're gonna have, or interesting problem, is just the size of turbines. So they're getting bigger and bigger. We expect them to keep getting bigger, and this just gives us more complex modeling problems. And and as well, we're going to come across floating turbines. So there's been a lot of floating wind in the news recently. So this is a really interesting modeling problem because the dynamics of a floating wind farm are just kind of crazy. So we need to be able to develop the tools to deal with those kind of modeling problems and to develop new models to solve those problems. Bigger wind farms too. So Dogger Bank, I mentioned earlier, 4.5 gigawatts, 400 turbines. So managing a project that size and predicting the maintenance becomes very important. You can kind of imagine that it's similar to a data center where hard drives are failing just all the time, like a big data center owned by like Google or Facebook. So turbine components are just going to be failing all of the time, just because statistically they're likely to. And finally, we are going to get more high frequency data. So this becomes then a data engineering challenge. How do we make the most of that data? How do we get that data from the turbine to the cloud, or do we use edge computing approaches to generate vital insights into that data at the turbine and then send it on? So this is a problem that we're going to be looking to tackle soon. So, final slide is just putting ourselves in the context of the rest of the energy grid. So we're pretty good at wind turbine and wind farm performance analysis, but that's really just a small part of the bigger picture. So we want to be able to connect to our data to data produced by other renewables, grid, the electricity grid, to storage, whether that's battery storage or like pumped hydro, for example. We want to maybe automate the maintenance of all of these assets. And we want to be able to respond to demand from homes and from factories. And also like integrate with energy markets to let them know how to optimally use the energy from a wind farm. And overall, the goal is to just lower the cost of green energy, because really we've got to stop burning stuff. Thank you.
Amazing, Mike. Thank you so much. Let's all unmute. I think you have to individually unmute. We can't unmute you all, but let's show our appreciation for Mike. Thanks very much.
Nick.
Great.
Oh, there's a dog there as well. Awesome.
So we're going to switch now to the Q&A, which Chris, you will curate via the chat, I believe. Is that the plan?
Yeah, I will. I mean, I don't really know what to say. That I found that amazing. And we've got loads of questions, but I think it's supposed to be a data-centric talk. So I'm going to go for the data. And I'm going to go for Ian Wallace, if I can find it in the morass of questions. Ian, do you want to unmute yourself and ask your question?
Sure. So my question is, I guess, what data do you wish you had on the turbines that you don't have? And expand that to be not just the turbine, but the monopilar jacket or export cables as well.
Yeah, well, I suppose it depends on what problem you're looking at. So we kind of wish that we had all of the data, and then it just becomes a data engineering problem. But I guess if we're going to prioritize, and if we're looking at something like predictive maintenance, then of course you want the signals from the components that are going to fail most often. So that's generally the moving parts, like things in the gearbox and inside the nacelle. So you want that high frequency data and all of that, like really accurate temperature data from there. But yeah, I mean, from my point of view, I would love to be able to provide our experts with all of the data, which is a bit greedy. But, yeah, did that answer your question, Ian?
Yeah, kind of. I think I could go into more detail, but I won't, because it'll probably rapidly get quite specific for most of the audience. But yeah, that was interesting. Thank you.
Yeah, so to be selfish and specific, I mean, are you talking to other people who run sort of server farms like Google and Microsoft and about replacing stuff when it goes wrong? And No, you're not hop?
We're not personally, but I have talked to people who are. So actually, one conversation I had was with a chap who works for a manufacturer over in China. They were working with Baidu, the like Chinese Google, who had machine learning models for predicting hard drive failure, and they were trying to apply exactly the same things to their wind farms because they've got just huge numbers of turbines that are going to have components that fail, and so yeah, I don't actually know what the specific outcomes of that were, but it's definitely a parallel that is worth kind of drawing.
Okay. So in terms of when things do go pop, if a turbine is really, out of commission, what happens to it after that? Or has that not happened yet?
It doesn't happen that often. Of course, they reach their end of life, and when they reach their end of life, it's generally before they've exploded. Like you do see pictures in the news from time to time of like turbines on fire, but that's so rare it's barely worth talking about. But when they do reach their end of life, they're dismantled, and that is a problem that the industry is facing. Is what do we do with turbines when they're no longer of any use? The components are difficult to recycle, but we have to continue working towards a solution there.
Okay. Mark Lazarides, do you want to unmute and ask your question?
Yeah, sure. Thanks, Chris. Thanks, Mike. That was awesome, by the way. So my question was, I think you answered it towards the end actually, was whether you're looking at moving any of your data analytics on board the turbine using a sort of cloudlet or edge computing pattern.
Yeah, we'd love to. It's not something we're actively doing, but I think we want to start conversations with the asset owners and also in the planning stage to get them get the right sensors in place and get the right computing hardware in place to do that. I think that at the moment there's a lot of talk about it, but there hasn't been a good proof that it's worth the value. But components are just getting so cheap that at some point it's gonna be worthwhile just banging a load of hardware on there and seeing what happens. So yeah, we just need the right kind of strategic partners in order to work with them and prove that there is value in that approach.
Cool. So we've got so many more questions here, but I think we need to move to the panel.
I think we've got time for one more, maybe.
Okay. Okay. I don't know which one to pick. Yeah, Jack, do you want to unmute and ask your question? Or I can ask it. So Jack says, what are the current biggest challenges for your customers that you're helping to solve or anticipate needing to solve?
I think the biggest challenges is around this predictive maintenance. So predicting when components are going to fail, that is probably the biggest cost that they're facing right now, and that's kind of the biggest opportunity in terms of lowering the overall cost. And so we're putting a lot of effort into developing kind of the models that we can use to make those predictions more accurate, and also then there's a wider question about how we use those insights when we get it. So how do we integrate with the systems and with the companies that do that maintenance, and how can we really firm up those predictions to make sure that we're not raising too many kind of red herrings.
Cool. So quick question from me. Who are the companies that are maintaining the wind turbines? Do they get in a boat to go to Dogger Sands, or?
Yeah, they will do. I mean, I'm not sure of names of companies, but I expect there's hundreds around the world. There's in terms of the offshore turbines. So Dogger Bank is interesting. So the plan for Dogger Bank is to actually build an island in the middle of the wind farm, so that the maintenance crews can live there. Well, the construction crews can live there while they're building the farm. And actually, I don't know if the plan is for the maintenance crews to live there as well. But the project is so huge that they think it's, and Dogger Bank. So it's this kind of very low sea level. I think it's about 30 meters or something like that. So it's but it's out in the middle of the North Sea. It used to be land, so there's like dead forests down there that just got swamped when the ice age ended. So it's a pretty cool kind of project.
Amazing. Okay, Mike. Well, thanks for answering those questions. We're going to move to the panel, if that's okay. I'm going to introduce another couple of people. So Lawrence Watson, who's a data scientist at Future Energy Associates. Lawrence, do you want to say hi so people can lock into your voice?
Hi, Nick. Hi, everybody. Thanks, Mike. That was great. I'd love to keep going through the questions. I think there's some really good ones there that are going to keep us going. Yeah, I'll just briefly. So, just briefly introduce myself. So, yeah, as Nick said, yeah, I'm part of a energy consultancy called Future Energy Associates. I've been doing sort of data and analysis around the energy sector for about 10 years, modelling power systems using satellite imagery to track coal plants, a whole range of different things.
Right. Thanks, Lawrence. And also, we're joined by Robin Abrahams, the head of product at Kaluza. So, Robin, just want to flag up your voice.
Hey everyone. Yeah, my name is Robin Abraham. I'm a head of product at Kaluza, which is a technology company essentially owned by the OVO Group, and we operate sort of two types of energy technology platforms. One is basically a technology platform for energy retailers, so which is aimed at simplifying and reducing the cost of operations for energy retailers, and kind of born out of some of the technology that was built for OVO Energy along its journey as a startup that was founded 10 years ago into becoming a bigger, more mature energy company. Cool. And the other technology platform.
If I can just stop you there, just because we've got to crack on, I do apologize for that.
Yeah, that's fine.
The question I guess I've got is raised from the talk, where it's kind of, Mike, you're saying that so data is a byproduct of operating wind farms. When do you think that data will be a kind of a first-class citizen, or is it in fact seen as an afterthought? Is that correct, or is that false?
You're muted, Mike.
Mike, are you on mute?
Yeah, I was on mute, sorry, and then I moved my Zoom window, so I couldn't find the mute button. But yeah, sorry, I was saying, I think historically data has been an afterthought, and I think the problems that we face is that almost every farm that we look like is to some extent historic, so we don't tend to get into the analysis stage of wind farm data until it's something like 5 or 10 years old. So if you go back that far, then definitely data was a very much an afterthought. I think these days wind farms and wind turbines specifically are probably built with a lot better sensing technology, and the data infrastructure is a little better. But actually, I don't really know. I'd like to kind of get into that and start to explore what is available to us on a modern wind farm, but it's just not something that we get the chance to deal with that often.
Okay, and I guess you've been focusing a little bit there on kind of the supply side, and we haven't really even touched on demand side optimizations and the other side of the equation. Does someone want to pick up on kind of what is the supply side, demand side here?
Yeah, I guess I can speak a little about that, but I guess fundamentally, like, the challenge of electricity and energy is essentially a balancing energy demand and supply problem, and balancing that across sort of multiple timescales, like kind of trying to predict down to the last second what is the exact amount of energy that you need on the grid, and supplying only that amount of energy. And traditionally, I suppose some of those forecasting and demand side optimization problems have sat with, say, a supplier's trading team, trying to make sure that they forecast the amount of consumption that happens in their portfolio, so that they don't, get penalized for bad prediction. But I think increasingly these problems are moving to kind of much real-time timescale, and so that basically means that we can move some of that decision making away from humans to kind of machines that are able to make decisions on what is the best time for say something like an electric vehicle to consume energy. And I think that's the world that we're like really entering now. And that means that, you know, we need to kind of be very cognizant of how we can have end consumers play a more increasing role in managing the needs of the electricity grid, and how can we convince them, and how can we get them to be part of this problem and really engage with it.
So I mean, can you give us some examples of kind of incentives then? Because like, presumably you need to incentivize both sides.
Yeah, definitely, and I guess so. One of the examples that I can give here is, because we were on the topic of wind energy, and you know, Michael had mentioned wind curtailment. So one of the early parts of my company was involved in was to show that you can mitigate some of the effects of this curtailment of wind energy by using essentially data from the turbine, data from the network, and weather data to predict how big the curtailment might be, and then turning up, say, something like an electric storage heater in a customer's home to kind of mitigate some of that curtailment. So instead of having to, you know, reduce its consumption all the way down to zero, maybe a turbine can operate at, say, 200 or 300 kilowatts because 300 kilowatts of electric storage heat has turned up. And this obviously, you know, means that you are not wasting plentiful energy, renewable energy that's coming onto the system, and instead directing it into these heaters, which, you know, these customers can then, in that particular project, they were getting that energy for free, but they could theoretically use that energy almost like a mini heat battery to kind of heat up their home at some point later. So I think that's like a very specific example, but obviously I think EVs is a big story here as far as demand side optimization goes, and you know, can keep talking about it, but if we come back to that, you know, can speak a little bit more about how we can use EVs for demand side optimization.
Okay. Well, do you think that the supply side, demand side distinction is increasingly getting blurred? Is it like, is it going to be a false distinction if, you know, if everyone has renewables on their houses, and actually we've got battery storage in cars or whatever? Is it a false kind of, in some sense, is it a false distinction?
I don't know if Lawrence or Michael, you want to take that question. I can chip in a little bit.
I wouldn't go that far, Nick. I mean, like one way to think about it is just to look at the structures, like the market structures that everything is operating in. And so there's a huge consensus around the need for more flexibility on demand side and supply side. So, for example, the local electricity operators, the district system operators, are now starting to do flexibility markets where there can be like local smaller energy assets can then bid in, but there's also a balancing market at the national level, which is about real-time balancing or short-term balancing of the grid. And even though wind turbines obviously are in some ways the reason for the need for extra flexibility, people are now saying, well, if a wind turbine has been constrained, is there a way that actually it could be available to participate in the secondary market, balancing market? If we can work out bring in if it was then turned on. And ourselves and Bitbloom, I think, participated in a hackathon with the offshore renewables catapult around that, trying to work out how we could better predict what the power would be if you went from zero to turning the turbine on, which is kind of a tricky thing. So there's lots of ways data is sort of coming in here, but I wouldn't go to say that demand and supply side are you know, completely overlapping.
But so presumably, if data is becoming such an important component of renewables, then access to that data is going to be increasingly important. So do open data standards exist in this area? Mike, you were saying that it's a bit of a mishmash. Is there any chance of open standards in this area?
Yeah, so I mean, from the kind of data that we deal with, there's as I said, there are a few open standards for things like data generated by machines, but that's pretty low level for what we like to deal with. So in terms of like doing the analytics on that data and getting kind of value from that data, there's certainly no kind of open standards, and I think what we'd like to explore as well is once we have that value for that data, once we have some insights into that data, you know, whether it's you know, we know that a wind farm is being curtailed this much and it's got so much extra capacity that we can provide to the grid, how do we then like make that data useful to the rest of the grid? And so,
to add to that, Pavel talked about
yeah.
We lost Lawrence. Okay, I think we've lost Lawrence.
Sorry, I went a bit roboty there, I expect.
To carry on, yeah, if you've got an answer.
I'll come back. Well, Pavel was talking about how the big manufacturers control a lot of the data and they offer a lot of these services, which is right. And so there is a question of how you can sort of open up the industry to small players and to innovation when there are a few sort of very large centralized manufacturers like Siemens and Vestas. And one answer is there is a big push from government called Modernizing Energy Data Access, which basically is an ask, and then for companies that have public funding, it's more of an instruction that they should dig into all of their data sets and work out everything that can be made open, should be made open. And the first step is categorizing everything and doing the cataloging. But that's going on at the moment. And that part of that is a standardization effort, absolutely, because yeah, there's a lot of competing sort of different standards. So it's a big effort.
But if you compare it to something like, open banking, there's a regulatory pressure to actually, conform and have the APIs. Do you think that we need regulation to actually impose this upon the industry?
I mean, to the extent that my experience with talking to asset owners is that they do kind of feel that why should they share their data if other people are going to use it to create algorithms to then compete with them? And so in that sense, I do sort of would broadly say that yes, there should be a regulatory pressure because mostly people aren't being collaborative with stuff, so they need to be made.
Yeah, I think, but just to add on to that though, I think I'd say that open data standards are not just about opening up the data for free access, right? It's about establishing protocols so that data can be more easily shared. It's about kind of ensuring that those people that offer up this data, they have a way to monetize that data. So it doesn't have to be for free, but what needs to happen is to ensure that some of these standards are set in place so that that sharing of data, that process becomes a lot easier, and then people who are in the middle, startups, can go in and say, well, if I pay for A, B, and C, I can get these data and I can provide a service, which is a higher value than pulling together those bits of data. So I think, I think regulation is going to play a part in that. I definitely agree with Lawrence that currently there is a kind of trend in terms of bringing standards for some of the data, but they are competing standards. So I think someone stepping in and saying, okay, let's centralize these standards, maybe even at a global level, I think could happen. And for example, in our field, which is essentially trying to control physical assets, every smart charger has a different way by which it communicates and takes commands. And if you wanted to, send on a command to, the 10 smart chargers that exist in the market, well, you almost need to individually integrate with each of them. And, that seems, waste of effort. And I think there's definitely areas where you can actually just have an open standard and make the smart charger company conform to those standards and make it easier for their for smart charging to be more available to the grid.
Yeah, the other thing that sort of strikes me is that given the longevity, like you were saying that wind turbines are 30 years plus, so presumably there's a lot of legacy systems here as well, and the sunk costs. So how are we incentivizing here about the value of having the data in the cloud and standardized, given that there's a lot of legacy systems that are in place?
Yeah, I mean the legacy systems we can deal with by retrofitting with better sensors or better communications technologies. So provided that there was an incentive there to do that retrofitting, then I think it would be a worthwhile kind of pursuit. And that incentive could just be that okay, if you want to play a full part in the energy grid, and if you want to get the maximum value out of your asset, then you have to conform to these these data standards. Then that might be just enough incentive to do those upgrades.
Okay. And finally, so we're running out of time, like a few minutes to go. I'm just wondering, is energy tech a thing? We've got reg tech and insure tech. Is this kind of like the nascent energy tech industry?
It definitely is becoming a thing, and I think because energy in many ways it's beginning to incorporate a lot more things. A lot more things are becoming associated with energy. So when we start talking about electrification of heat and storage, suddenly, electric vehicles and batteries, all of these things come into the picture. So I think, how can you control all of these things for the benefit of the grid? And I think that's slowly making big established players from the auto industry, from entering this market and looking at technical solutions. And you sort of obviously also have, incumbent players in the energy markets looking at electricity as a place where a lot of their fuel supplies are going to go to. So they're interested in investing in this area. So I think definitely it's becoming much more of a thing, and that's certainly what I see. And there certainly are, what was a niche conference a couple of years ago is becoming a bit more mainstream, and there are a couple of instances of that out there.
Okay. And any final comments from Mike or from yourself, Lawrence, before we close on that?
Oh, I totally agree with Robin just on that, because it is quite an exciting time over the last 10 years to see there's huge changes going on. Robin's exactly right about why it's more of a thing, because everything is being electrified or decarbonised in other ways, but a vast amount of things are being electrified and made smart and digital at the same time. So an absolutely enormous amount of increased data, of increased control of all these things, and they're all interconnected, and that means vast amount of room for innovation, loads of creativity, a lot of data and engineering being brought to bear, and ML and AI injected in a few places. I would say there haven't really been that many big wins yet in terms of using sort of applied machine learning, in terms of very high profile things. I mean, I know, DeepMind tried to use their algorithms to optimize wind turbines, and they didn't have a huge amount of success, but I think it's coming, and part of that is because the sort of baseline level of digitalization isn't quite there, but it's sort of coming along pretty quick. So yeah, really very exciting time.
Mike, any final thoughts on that?
Yeah, no, I definitely agree, and I think we've all probably heard of green tech, which is probably what perhaps we think of ourselves as, but I think we really want to be part of N tech, or energy tech, and I think that it comes back to just making this greener future that we all want, and it's becoming abundantly obvious that we can only do that by integrating in a really smart way with the rest of the energy grid. So we can't kind of just be siloed as green technology. We really have to work with everyone who's involved in the grid.